All right, let's get started. So just to remind you where we are still in the midst of discussing energy methods. And for the most part, as you know by now, these energy methods give us ways to approximate solutions to various structural engineering problems. And we've covered a bunch of different ways to approximate things. We've covered Castigliano's theorem. We've covered just the sheer scaling of kind of balancing energetic terms in the system. Last class, we looked at how to solve beam deflection problems using a substitution by Fourier series or other trigonometric series. This is something we demonstrated on a beam, but it's something that is readily used when people are trying to analyze plates or shells. I was actually doing, while working on research yesterday, was working on a problem of a deforming spherical shell, and you do a very similar thing in the case of a spherical shell, except instead of using a trigonometric series as your substitution or your guess, you end up using what are known as spherical harmonics, which are basically another set of kind of periodic functions, except those live on a sphere instead of something that is kind of a wave that lives on, I think of it as living on a line. And there's kind of different times that you'll use different techniques, and some of it depends on how easy or difficult it is to, for instance, guess a function. You recall last class when we started with the simple trigonometric series, it was really easy to do when you just could guess the Fourier sine series, put that in, and calculate the solution. And then we saw for the second half of class that when we wanted to do a cantilever beam, we had to do a lot of work to guess what the function was. And so what we're going to talk about today is another way to approximate problems. This is what's known as the Rayleigh-Ritz Method. It's really, really commonly used in structural mechanics for a couple of reasons. One, you don't have to guess the shape of function perfectly. You can still get a good approximation, even if you make a pretty bad guess. Two, it's really useful for solving problems of stability. It's really good at basically anything that has to do with eigenvalue problems. And so stability problems, like when something's going to buckle or when a complicated structure that's got multiple components is going to buckle, can be solved using the Rayleigh-Ritz method. It's also in a lot of ways kind of the ancestor or kind of precursor to the finite element method. It's a little bit more robust and can be done a little bit in different circumstances than, say, the finite difference method or some other numerical methods, like, for instance, a shooting method, which turns a boundary value problem into an initial value problem. The Rayleigh-Ritz method can handle boundary value problems with approximations of the shapes that we're going to use, and able to provide pretty good estimates for either deflections or buckling loads and such like that. And so this is a really commonly used method. I use it all the time in my research. I encounter it a lot when I'm reading papers. And so I think this is a really important one for us to spend some time on. And so this is what's known as the Rayleigh-Ritz method. And I'll first kind of give you the kind of a qualitative like order of operations, if you will. And so the procedure goes like this. It looks very similar to what we did last class. So the first thing we're going to do is we're going to assume / guess an expression for the shape. So we're going to only talk about the shapes of deflecting beams just to demonstrate how this procedure works. So you could think about when I say assume or guess the expression, what I'm saying is assume some sort of function that is going to be describe the deflection curve of the beam. This is often done in the form of a series with unknown parameters. And our goal, just like last time, is to determine these parameters, this kind of a sub n, this unknown parameter a that for each term in the series will have a different value. Okay, so once we have this shape, now the expression that we guess is less restrictive than in the trigonometric series. If you remember last class, when we were guessing a function to be used that will apply the principle of virtual work and that will use to guess the shape of the beam, it needed to match all the boundary conditions. Here we are a little bit less restrictive. The series only has to satisfy the kinematic or geometric boundary conditions. Okay, what does that mean? What that means is we're talking, it must satisfy displacements. So that means, what the value is of W at, for instance, the ends So for example, what the value is, this would need to be satisfied, and it must satisfy the slopes. So again, for example, we need to be thinking about the first derivative of the deflection at some points. But it does not have to satisfy what are known as the natural or static boundary conditions. So these are what you would think of as forces and moments. Now, I should say, and I'm going to make this point really clear because we're going to go through a specific problem. If you pick a function that does satisfy all the boundary conditions, it will be much more accurate than if you pick one that only satisfies what I've written in red here, those kinematic or geometric boundary conditions. So if you just do the kinematic and geometric boundary conditions, it will work and you will have a pretty good amount of error compared to the exact solution. And if you're satisfied with that, if you just need to get some sort of approximation, that's fine. If not, then you'll want to pick a function that satisfies the natural or static boundary conditions as well. And you'll see here that when we do that, we get a better approximation for the solution. All right, now what? Step 3. So step 3 is we're going to write out the total potential energy. Yeah. And this will be written out in terms of our unknown coefficients a sub n. once we have that, the application of the Rayleigh-Ritz method is to simply take, let's say that a total potential energy here, hold on, let me show you this thing. For the sake of this class, we're going to write this as capital pi. And so if we write this, the Rayleigh-Ritz method is requiring that the potential energy must be a minimum at equilibrium. Potential energy at equilibrium. So what does that mean? It means, well, let's do this in red here. So application of the Rayleigh-Ritz method often looks like this. We've written down pi, and then what we're going to do is take the partial derivative of our total potential energy with respect to all the unknowns that we keep. So A1, that must equal 0. The partial derivative of pi with respect to A2 must equal 0. All the way up to however many terms we decide to keep in the function, which will dictate how much accuracy we want. These will typically lead to a set of algebraic equations that you can use to solve for an. So we can use these relations, use these to solve for a sub n, and then put that back into our guess for the deflection curve. Now I said something here, and I'll make this point clear again in a moment. In the trigonometrics, the solution by trigonometric series that we talked about in the last video, in the last lecture, what we said was that if you pick a good function and it satisfies all the boundary conditions, then if you keep an infinite number of terms, you will converge to the exact solution of the problem. Here with the Rayleigh-Ritz method, if you pick a function that only satisfies the kinematic and geometric boundary conditions, you can take as many terms as you want, you will never converge to the exact solution. If you pick a function that includes both the displacement, slopes, and your natural and static boundary conditions, so if your function satisfies all the boundary conditions for your curve, at that point, if you keep an infinite number of terms in your series, you will converge. So this is a little bit different. It's important for you to know when you pick a function, does it satisfy all the boundary conditions or just those geometric or kinematic boundary conditions? Because that will kind of tell you how many terms it's worth keeping. It's not worth keeping 50 terms if you're not converging towards the exact solution anyway. So again, the accuracy of this method is going to be dictated by how good the approximate shape is and does it satisfy the boundary conditions. So this is the approach. Here we're not relying on the principle of virtual work. We're actually going to use the total potential energy, the strain energy, and the work in their actual forms instead of in their kind of perturbed variation forms. That'll make more sense in a moment. But this is our procedure that we're going to follow. And we'll try this thing out on a single beam that's simply supported. Okay. So let me draw this thing. Ah. So there's our beam. We'll put this under a distributed load, so some force per unit length. This distributed load, we'll call it Q. In this case, I've had Q to be uniform. We'll denote our coordinates as we usually do, such that this is X, and this is Y. Y is positive down. And let's see here, we'll make the length of this beam W. And we'll try to calculate the deflection of this curve and determine what the, let's say, what is the maximum deflection of this beam. So what the first thing I'm going to do is I'm going to tell you this is a trivial problem. This is something that we have done before. You could solve this just by writing out the differential equations for an elastic beam, applying the boundary conditions, solving it, and you can do this in a very straightforward manner. And I'm pointing that out just to I want us to be able to know that there is an exact analytical solution here, and we can use our approximate methods to compare and see how it's doing. So for instance, the exact solution here is W max. Exact. I'm not going to go through how to calculate this. This is something that you've done in prior coursework. The exact solution, and I'm going to approximate the denominator here, but we're going to write it as Q L to the fourth, and I'll keep 76.8 times EI. So this is what we want to see. We can check our method and we can compare it to this one. So what we're going to do is use the Rayleigh-Ritz method. We're going to do it twice, the same problem twice. The first time we're going to just satisfy the kinematic and geometric boundary conditions. The second time we're going to satisfy all the boundary conditions, and we'll see how this does. So for the case of picking a function that satisfies just the kinematic and geometric boundary conditions, we can look at a power series. And here's something that in a little bit, when we start talking about the finite element method, we'll be able to see that this kind of seems pretty similar, in which you have these nodes and you're kind of picking some function to interpolate between them, and usually the simplest thing you pick is a power series. So we're gonna say, let's try a power series. Why? Because it's easy. It's just polynomials. It's really easy to take derivatives of. So we could say, let our deflection, W, which is going to be a function of X. So if you remember step one is guess an expression, and this should have some unknown parameters in it, A sub n. So we're going to guess that our function is a power series. So we'll say W of X is going to be equal to A sub 1 times X L minus X plus A sub 2 X squared L minus X squared, and so on. And this can be written more compactly as the sum from n equals 1 to infinity. I'm going to write that a little bit cleaner. The sum from n equals 1 to infinity of A sub n times X to the n times L minus X raised to the N. Why do we pick it in this form here where the power series has X times L minus X? You can see that pretty quickly when you check to see what happens at the kinematic boundary conditions here. So what happens with the displacement? So here we know nothing about the slopes at each end, right? This thing is going to be simply supported, so it's going to have some slope there. We don't know what it is, so we don't have any restrictions on what that slope would be. The only thing we know is that there can't be any deflection at x equals 0 and at x is equal to L. And so if you take this thing and you say, well, what happens at x is equal to 0? And pretty easily you see that this is 0. And if you take the deflection at W of L, now you can see why we wrote this as we did, because L minus L is 0, and again, we get 0. So check, we satisfy that's terrible. We satisfy the kinematic boundary conditions.
But does this satisfy the slope condition?
So good question. So we don't know anything about the slopes. So there's actually no condition on the slopes for this equation. So if you remember, if you were to solve this exactly, we would know we know that there's no displacement, and we know that there's no moment or no second derivatives at the edges of the beam. But the moment is a natural or static boundary condition, because really what you're saying when you say you know something about the curvatures at a point is that you're saying you know that there is no moment being applied there. And so whenever you're saying something about moments or forces, then you're looking at the natural or static boundary conditions. And for this method to work, you don't have to satisfy those.
Okay.
If this was a clamped beam, we'd have to pick a function that satisfied the deflection and the slope. Okay, so we're going to be really lazy, and we are just going to consider the first term of the equation, just so we can make this really simple. So we're only going to look at this one. Okay. So recall now our goal. So we've done step 1. We've guessed a function. It's got unknown parameters a sub n. We have done step 2, where we made sure it satisfied the kinematic boundary conditions. Now we have to do step 3, which is write out the total potential energy. And so remember that our total potential energy is pi, capital Pi, which is going to be the strain energy minus the work being done. Okay. So this strain energy, we know this beam is only bending. The only contribution to the strain energy for this deflecting beam should be the bending component of the strain energy. So it's going to be like EI over 2 times the integral of your curvature squared. Okay, so that looks like this. So we're going to have the integral. I'm going to move this thing down so we have a little bit more room. So we're going to have the integral from 0 to L of EI over 2 times the second derivative of our deflection. And recall that this term is squared. And we're going to take away the work. And that work is going to be the force per unit length times the displacement of the beam. So it's going to be our Q times W of X. And this is going to be integrated along the length of the beam. So just to recall, this is U. This is W. And this is really straightforward to evaluate here. So here's the moment where you can see how powerful the Rayleigh-Ritz method is, because we're being incredibly lazy and we're going to get an approximate answer pretty quickly. And because we chose polynomials, it's really trivial to kind of calculate these derivatives. So okay, let's look at our term here. So again, we're going to integrate from 0 to L. EI over 2. Now the second derivative of this first term in the polynomial is just simply going to be negative 2a1, and that's going to be squared. You can check yourself to make sure that that makes sense. And we're going to take away, now here we're not taking away any derivatives of w, we just need w exactly. So it's going to be a1 times q times x L minus x. So you can probably do this integral by hand pretty quickly. I'll just tell you what it is as it gets evaluated. So our total potential energy pi is going to be, here's the integral before we evaluate the range on x. It's going to be EI times a1 squared times x minus a1 over 2 times qx, let's see, squared times L plus a1 over 3 times qx cubed. And that'll be evaluated between 0 and L. And once we evaluate that, we end up with 2 EI times a1 squared L minus a1 q L cubed over 6. Okay, so now we have written out the total potential energy. This is step 3 here. And the final step in this process is we don't know, we need to figure out what A1 is. And so to do that, what we'll do is we will take the partial derivative of pi with respect to A1. That's the only one in this problem. We didn't keep A2, A3, A4. So we just need to take one derivative of pi with respect to A1. And we need to set that equal to 0. So this derivative here is going to be equal to, let's see, we have the A1 squared, so it's going to be 4EI A1 times L and for the second term, we're just going to have minus QL cubed over 6. And we know we have to require this to be at equilibrium for us to be we have to require this to be equal to 0 for us to be in equilibrium here. And so we can pretty quickly solve for A1 here. So if I want to solve for A1 is simply QL squared over 24 EI. And our final step is to put that back into W of X. And if I actually want to compare this with our analytical solution for the maximum deflection, we'll note that the maximum deflection is going to happen at the center of the beam. So if I want W, well, let me write this out actually. Therefore, let me just write out W of x first. So therefore, W of x is simply QL squared over 24 EI times x L minus x. And finally, what we can do is we can look at the max deflection. And that will occur at the midpoint of the beam, so at L over 2. And what we get there is that it's Q L to the 4th over 96 EI. Okay, so not too bad. So we guessed a series to describe the shape of our beam. We picked a power series. We kept one term. We made sure that that power series satisfied the kinematic boundary conditions. We put that into total potential energy, evaluated it, and then required the total potential energy, required the system to be in equilibrium. So this right here is really an application of the principle of minimum potential energy. The total potential energy must be at a minimum, so therefore derivatives of that energy with respect to these displacements, which are going to amplify that total potential energy, that must be equal to 0. That allows us to solve this equation pretty simply, calculate our unknown coefficient, and therefore get our shape and our max deflection. Now, comparing this with what we had before, yes?
I didn't understand how we choose the WX series. I mean, we just tried with this one, or we have?
Yeah, we just tried.
Okay.
So you basically want to pick some sort of a series in which you have some unknown coefficients and you have some behavior of that series along x. And you can choose any series. The last class what we focused on was trigonometric series. So we would always pick like a Fourier series. We would say W of x is going to be equal to, say, the sum of a sub n times a sine of n pi x over L. But that's a more complicated series. Evaluating the integrals and derivatives requires a little bit more work than like the 3 lines we did here. So the simplest thing you can do is choose some sort of power series. So a power series is basically just saying, let's pretend we can pick a curve that can be described by polynomials, and all we need to do when we pick a curve that can be described by polynomials, so we can't just pick, say, so a bad power series. Let's see, I'll do this over here. Let's write this in dark green. So a bad power series, your first guess might be, all right, well, I want to just the simplest power series I can write down. The simplest power series I can write down would be W of x equals a sub 1 x plus a sub 2 x squared plus a sub 3 x cubed, and so on. And what you'll notice is that W at 0 equals 0, but W at L is not equal to 0. So therefore, this power series does not satisfy the kinematic boundary conditions because we know this thing cannot displace at W of x. And so the simplest power series that does satisfy these constraints is one where we ensure that when x is equal to 0, w is equal to 0, and when x is equal to L, w is equal to 0.
Okay.
Does that make sense?
Yeah, yeah. Thank you.
Okay. This is just an example. We're going to solve this problem a second time, but with a different series expansion. But I'll tell you this. There's basically all right. So more often than not, anytime you're seeing these approximate methods being used, people are either guessing a power series or a Fourier series. Now, in some more complicated geometries, you might encounter people using more complicated series expansions like Chebyshev polynomials or spherical harmonics, other functions that behave well in the geometry you're in. But most of the time, you're basically going to either see some sort of a power series that looks like this and is chosen such that it matches the boundary conditions, or a Fourier series. So those are the things that you can, so at first, when you're first encountering this stuff, this all looks like someone pulled some magic equation out of thin air. But it turns out that once you kind of are comfortable working with power series and Fourier series, these are the ones that most people use for structural mechanics analysis to approximate things 90% of the time. So if this is unfamiliar at the moment, just kind of understand that we picked a power series because it's easy to work with, and we just had to make sure it matched the boundary conditions. But you'll see, going back, that, let me go back over here, I'll write down let's write down our exact. Now we have a lot of error here. I'm just kidding. This has 17% error. And now whether or not that's a good or a bad thing depends on your problem and the level of accuracy you need in your problem. If you know you have a bunch of other terms that are contributing around 20% error, then you don't need to do much better than this because you're kind of trying to perfect something that's going to be imperfect anyway. But if it's something you need to have much closer precision, this is not going to be adequate. And as I said before, when we did the trigonometric series, we could just keep more terms. So we could just keep, say, instead of keeping only this first term in the expansion, we could go back and we could keep the second term in the expansion and do this whole process again, solve for A1, solve for A2. And you'll start to notice that if we keep two terms, we start to have a system of equation that we need to solve. And so instead of just solving the partial derivative of pi with respect to A1 is equal to 0, we're going to have two equations with two unknowns that are going to be partial pi, partial A1, partial pi, partial A2, solve for A1, solve for A2. And here's where, again, I would point us back to using Mathematica so that we could solve these system of equations when n is more complicated than just one or two. But the point I want to make is keeping more terms is not going to make our answer converge to the correct answer. And it's not going to do that because this equation does not match the natural or static boundary conditions. The power series we chose doesn't match our natural or loading boundary conditions. And so it'll never converge to the exact solution. So if we need to do a lot better than this 17% error, then we need to pick a different series. It's one that matches not only the displacements and slopes, but also the forces and moments. How are we doing on this? Are people feeling comfortable here?
So if we choose a series also for the moment and the forces, we have two different series, one for the W, and one for the forces, or just the same one?
No, good question. So it is not that we're going to choose a second series that's going to satisfy the forces and moment conditions, and we're going to keep this series that satisfies the displacements. What we want is to choose one series that will satisfy all the boundary conditions.
Okay.
Now, sometimes that's not easy to do, or maybe really unclear of what series would do that, and which is why this method can be really powerful, because if you can't guess a series that satisfies all the boundary conditions, then you can at least try to guess one that satisfies half of them, the kinematic or geometric ones. But if you can find a series that works for all the boundary conditions, the solution will be a lot closer to the exact one. So let me show you that by example. So I'm going to go back up here and just note that this was our first guess. So now we'll come down here and we'll work on our second guess. And here we're going to use the simplest Fourier series. If you're not comfortable working with Fourier series yet, I'll try to do a little bit of a review as I'm working on here. But remember, we talked a lot about this in the last video, and that video will be up online this afternoon, so you can get caught up on that if this is not comfortable. Okay, so the simplest Fourier series, as we saw last class, was to choose a shape W of x, which is the sum from n equals 1 to infinity of a sub n times the sine of n pi x over L. And here you can immediately see two things. One, W at L and W at 0 equals 0, right? I put in x is equal to 0, sine of 0 is 0, x is equal to L, sine of n pi is going to vanish. So we automatically satisfy our kinematic or geometric boundary conditions. The other two boundary conditions we need to solve this problem are being imposed on the edge of the beam as well, and these are the fact that there is no moment being applied at W of 0 and W of L. And no moment, as we recall, is related to the second derivative of W. So here, again, we can really quickly check second derivative of a sine function, first derivative goes cosine, second derivative goes back to sine, and again, we're okay. Second derivative of deflection at 0 and L, oops, is also 0. So we have satisfied the kinematic, and the natural boundary conditions. So here you can see that we have a guess for our solution that's already, we can just assume is going to do a lot better because it satisfies all the boundary conditions. There's no deflection, there's no moments. Okay, so again, we got to repeat this process. I did this last class, but I'm gonna do it again, just so that way you can let's see here. Yeah, there we go. Where did I lost Zoom? I'm gonna do this again so that you can remind it here, because there's a little bit of tricks. The use of Fourier series and trigonometric series are really powerful in guessing the shapes of beams and plates. And part of that power comes from the fact, I mean, obviously you can see here that if you pick the right one, they satisfy all the boundary conditions, so that's really good. The second part of it is that these Fourier series have these orthogonality conditions that make evaluating The integral's really straightforward. Now, this is true in a lot of cases. The work I was mentioning before, I was doing some work with spherical shells where we're using spherical harmonics, and the same approach applies. In these spherical harmonic systems, there are these orthogonality conditions between the shape functions that make it really easy to evaluate these shapes as you integrate over a surface, or in the case of what we're doing right now, integrating over a beam. And I'll go through that again. This will be a review from what I talked about last class, but I think it'll be helpful. Okay, so what do we need to do? We need to write down the total potential energy. So again,
Professor?
yes.
I have a question.
Yep.
Now our function satisfy also the natural condition. Are we sure that the function is going to converge, or there's a better chance that it will?
So in this case, if it matches all the boundary conditions, this solution will converge as if you take n to equal to infinity. So that, and there's a lot of work that was done in the mechanics community, this world of what they called rational mechanics, to ensure a lot of the tighter connection between the clearly applied mathematical methods here that you might see in applied math classes or advanced calculus classes. A lot of those efforts were done to on the mechanics side to ensure things like this will converge to the exact solution here. And so if you match all the boundary conditions, your solution will converge if you keep an infinite number of terms in your series. So here we know if we're going to do the same thing we did last time, which is we're just going to keep we're going to keep all the terms, but we're just going to check one term. And you're going to see two things. One, it's really close to the exact solution, and that's just with one term. So keeping more and more would tend to converge to that analytical solution. People have shown this and are able to prove this. We're not going to do that here, but yes, if you match all the boundary conditions, then if you keep an infinite number of terms, you will get the exact solution.
Okay.
Of course, you can't. The series itself isn't going to converge, so you kind of numerically have to pick how many you want to keep, but you are tending towards the exact solution.
Okay, thank you.
Okay, I want to just remind you of that orthogonality condition. So I apologize if this is review. We'll start with, so we need total potential energy, which means we need pi is equal to U minus W. And we're gonna just look at our strain energy for a moment. And let's do this right now. So our strain energy EI over 2, 0 to L, second derivative squared, integrated over dx is going to be equal to just to remind you all, we're in your textbook, we're working in chapter 10 right now on these approximate energy methods. So if you want to go and review this beyond the lecture and these notes, you can do that in our textbook. Okay, so we're going to put our series in here. So I'm going to take the two derivatives, and all that really does is returns the sine term and pulls out this pulls out the term multiplying x in the function. So this looks like a sub n times n pi over L times the sine of n pi x over L all squared integrated over dx. Now, you might recall that to deal with this squared summation, what you typically do is introduce another factor that you're summing over. So instead of saying I'm going to take this sum and square it. What we're really going to do is I'm going to sum from n equals 1 to infinity and sum from m equals 1 to infinity of each of these terms split up. So that'll make more sense as I write it out. But what I'm going to do here is I'm going to just look at, actually, let me erase this here. What I'm going to do now is just look at the term, the bracketed term. And I'll write that out in orange. So this term that I've bracketed in orange here, we're going to write out this squared term that includes the summation as two different summations. So we're going to sum from m equals 1 to infinity and sum from n equals 1 to infinity. And now everything gets doubled. So instead of an squared, you have am times an. An. Instead of n pi over L squared, you have m pi over L times n pi over L. I think those terms are not squared. Oh, that was already, sorry, that should have been squared here. Aha. Sorry, this should be squared right there, which means each of these terms is squared. And that's because we took two derivatives. Okay, continuing on, again, we're going to have sine m pi x over L times the sine of n pi x over L. Okay, so all we did is really just expand that squared summation term, and we did that by introducing a second term to sum over. The reason why this is done is it's really helps illustrate the properties of orthogonality in these trigonometric series. And that is because if I take, let's see here, if I just look at this function, and actually, let me just be clear with my notation. This is not equal. I'm just saying, let's look over here at just the, and I'm going to do the same here. So I'm not going to say equals. I'm just going to say, let's look at just the term in the green bracket. So if I look at the integral from 0 to L of the sine of m pi x over L times the sine of n pi x over L, there are two options. So one option is m and n are not equal to each other. And if you go into Mathematica and you plot from 0 to L this equation when m and n are not equal to each other, you'll get a function that looks like this. And you can pretty clearly see that if I'm integrating under the curve here, that when m is not equal to m, that this integral equals 0. Likewise, if you do the same thing, but you require that m is equal to n, we can plot this again. And you can do this in Mathematica. If this isn't making any sense or you're kind of confused, just literally go in to Mathematica and type, ask it to plot these two sine terms multiplied by each other. Take m equal to n and take m not equal to n, and you'll get these functions. And you'll be able to pretty quickly see that you end up with something that looks like this. And so the top one should be clear to you that it's equal to 0. The bottom one is not going to be clear to you that what the answer is, but it should be clear to you that that area is not 0. And what you find out is that this integral of this area over dx is equal to L over 2. So let me just kind of collect this and make it look a little bit nicer. So this is the orthogonality that people talk about when they talk about these Fourier series. So what that means is we know that m has to be equal to n, otherwise this integral vanishes. And we not only know that, but we know that once m is equal to n, this integral can be evaluated directly as, oops. Therefore, this integral equals L over 2. And we can go all the way back to what I was doing before. So using all of this, we can go all the way back over to here. And we can say that this means that U is equal to, I'm basically taking the L over 2, and I'm taking here that, I'm taking here that m and n equal to each other. So this becomes to the fourth. My strain energy becomes pi to the fourth EI over 4 L cubed times the sum from n equals 1 to infinity of a sub n squared n to the fourth. Okay. Questions? Is this making sense? Okay. All right. Good. Okay, so that gives us U. We also need W. So let's see here. W is straightforward. We can actually just simply, if you can do this integral out by hand, or you can simply go into Mathematica and ask Mathematica to calculate this integral, what's the integral? The integral is going to be, I'm going to integrate from 0 to L, the sum from n equals 1 to infinity of a sub n. I should put the q out front here. I left the q out, so the q will be here. Q times this integral sine of n pi x over L. And this integral can be evaluated directly and is going to be equal to negative L over n pi times the cosine of n pi x over L. And now I'm not going to evaluate this yet. I'm going to leave this as a indirect integral here, where I've not evaluated the bounding terms. And here's why. So I have this term here. I can So I can kind of go back and say that, all right, my work is going to be, oh, I lost the Q, didn't I? I'll put the Q out front here. Okay. I lost the summation as well. Let's see here. That's okay. I can put that in. Oops. Let me just, sorry. Your notes are probably going to look a little bit worse for the wear. I can put my summation out over here. There we go. Okay. So now I can go ahead and I can expand this out. And the reason why I'm going to do this is I can, let's see here. All right. So far I haven't done anything special. I've just literally evaluated this integral. I can expand this thing because I'm going to consider, all right, consider, you know, when x is equal to L and when x is equal to 0 to evaluate the bounds in this integral. And if I consider the bounds in this integral, this term becomes Q times L over pi times 1 over n a sub n cosine of n pi. So this term here corresponds to x is equal to L. And then minus Q L pi n is equal to n from 1 to infinity of 1 over n a sub n. And this is the term corresponding to x is equal to 0. The reason why I'm doing this out really deliberately is to point something out to you, which is that if I take any even number for my integers, then this term is going to be equal to 1. If this term is equal to 1, then you can pretty quickly see that this term would go away. And then this whole summation here would be equal to 0. That doesn't make any sense. We're asking what the work is being done to our system. The work can't be 0 just because we chose a term in our series of an even order. That doesn't have any physical meaning to it. So that means we know that our term n has to be odd. We can only keep the odd terms in the summation here. So this implies we can only keep the odd terms. And in that case, we end up with the cosine of n pi will equal -1 every time. We've had a lot of sign switching here. You know, this led to a negative, and now we're back. So a negative and a negative is a positive, and now we're back to only having negatives. So in the end, it's still going to look like u minus this thing, but there was a lot of sign switching along the way. So just kind of keep that in mind maybe when you're reworking this. Okay, so that means we can write our work term as Q. Actually, let me do this a different way. As 2Q L pi times the sum from n equals 1, 3, 5 of a sub n over n. And putting that all together, we have U, we have W. And so now we can write out the total potential energy. So you can already see a couple of things. One, we're going to get a better answer because we matched all the boundary conditions, but it's clearly taking more work. But the good thing with these types of trigonometric series is you start to recognize these orthogonality conditions, and you're like, okay, I've got sine, so that means I can take either my terms in the summation to be equal or not equal. What happens when they're equal? What happens when they're not equal? And you can usually reduce the complexity of the problem by using that orthogonality condition. So that just kind of becomes common and repetitive. Okay, so now we can write down our total potential energy, which is going to be equal to pi to the 4th EI. I'm going to make some more room here.
Excuse me, Professor, I got a question.
Yes.
Why we don't have the summation sign in the first term of the work where we expanded the integral?
Oh, that's just me being sloppy.
Okay.
So that's a good point. Good point. How can I do this without it being too much of a mess? Okay. I can move all of these terms. And I'll put in, thank you for catching that, the sum. There we go. That should be right. Is that, yeah, that's right now. Sorry about that. Thanks for catching that. Yeah, that was just me being sloppy. Okay. And pi to the 4th EI over 4 L cubed times the sum from n equals 1 to infinity of n squared, a to the n squared, n to the 4th. So that's my strain energy term minus my work term, which is 2q L over pi times the sum of only the odd integers of a sub n over n. Okay. Now we have our total potential energy. Now we move on to the next step in our procedure. We've got to require that the partial derivative of pi with respect to an is equal to 0. So we need to require partial derivative of pi with respect to a sub n is equal to 0. Okay, so we can do that. So the partial derivative of pi with respect to a sub n is equal to pi to the 4th EI times over 2L to the 3rd power times the sum from n equals 1 to infinity of a sub n to the 4th. And then we're going to take away, again, we have to differentiate this part of the equation, 2ql pi times the sum from n equals 1 to infinity, of all the odd numbers of 1 over n, and we have to require that this is equal to 0. You can usually tell if you've done these problems right if you have multiple terms and your equation is equal to 0. So there's an an here. There's not an an in the second one. If you look at our last problem, we had an an squared and, sorry, an a1 squared and an a1, so we're going to be able to solve for our unknown. If you don't get this, then you likely did something wrong. But here we can solve for a sub n. And we end up with that a sub n is equal to 4q L to the 4th EI over n pi to the 5th. And this is only valid for odd ends. Okay. So,
Hey, Professor.
yes.
The series that you have, I guess it's the derivative of work. Doesn't that series diverge? Yeah, the 1 over n.
I think what you're going to see is that because this is 1 over n, I think what you're going to see is that our deflection is actually going to converge, and it's going to converge really rapidly, because what we end up having is a sum where you have each term has got 1 over n, and now it's an odd n, so it's going to skip to the 5th power. So that very quickly becomes 0.
Oh, okay, okay.
That makes sense? You'll see
Yeah, I
that.
see.
I'll write this out now. So for instance, what do I want to do? I want to say, okay, let's go now that we know A. What I want to say is,
Oh, I see it now. I see it now.
okay, perfect.
Yeah.
So for instance, if I want to know the max deflection, then I'm looking at my Fourier series is sine n pi x over L, but I'm interested in this at x over L, which means I'm interested in the sine of n pi over 2. And you'll start to see that this sequence is I'll just point this out because it would cause some confusion if I don't. If when n is odd, you end up with this being equal to 1. Oops, nope, sorry, just kidding. That's not correct. That's not correct. Let me write this a different way. Sine of pi over 2 is equal to 1. Sine of 3 pi over 2 is equal to -1. Sine of 5 pi over 2 is equal to 1. Sine of 7 pi over 2 is equal to -1. So what you're going to see is that our solution for the max deflection is going to have, depending on how many terms you keep, each term is going to alternate signs. So let me write that out in a more clear way. My max deflection, so my W max, which corresponds to at x is equal to L over 2, will be equal to my a sub n term, so it's going to be 4q L to the 4th EI pi to the 5th. I'm going to take out that n, and I'm just going to put it over here. So it's going to be 1 over n to the 5th, and I'll keep, for instance, the first 3 terms. So 1 over 1 is 1. That's going to be 1 minus, and that's due to this sign change here. 1 minus 1, 3 to the 5th plus 1 over 5 to the 5th. So this is quickly converging. If actually, I'm going to write this out really quickly over here for you. So because of this fact over here, you end up with 1 over n to the 5th sine, oops. Okay, so let's just keep the first term in our equation. Let's just keep this term and compare. And if we just keep that term, W max with our Fourier series with only one term is equal to Q L to the 4th over 76.5 EI. I can hear your oohs and ahs from around the world. So that's pretty good, right? That's pretty good. Compare that to the exact solution where we had, what was it? W max exact, I think was QL to the 4th, 76.8 EI. And we have a really small amount of error here. And that error can be resolved by just keeping more terms in your equation. Let's try that again. All right. Now, there's a couple caveats here. One of those caveats being the series are not guaranteed to converge this quickly every time. This happens sometimes depending on the problem and sometimes not. Sometimes you'll need to keep more and more terms to actually get the solution converging to some constant value. But this kind of shows you that picking a series that matches all the boundary conditions, while it took a lot of extra work in terms of the calculation, yielded a much more accurate result. And two, if you take more and more terms in this series, you're actually going to converge to the exact solution. And you can kind of quickly see that here, that we're really close to the exact one. Keep the second term, and you're going to see that it's going to look almost indistinguishable from the exact solution. And so, as I mentioned at the outset, the trick with the Rayleigh-Ritz method is that accuracy is determined by how good the approximate shape is, and does that approximate shape match all the boundary conditions. All right. Questions?
Can you please repeat why n should not be even?
Yes. So you're talking about here.
Yes.
Okay. So look at this term. So let's see here. It should be clear, I hope, that this and this are the same, right? The stuff I've highlighted in the green are the exact same terms. And so if n is even, the cosine of 2 pi is 1. Cosine of 4 pi is 1. Cosine of 6 pi, et cetera, is 1. So if this term I highlighted in yellow is equal to 1, then the difference between the left term and the right term is 0. And that doesn't physically make any sense, because that means that if we're trying to guess the shape of our curve, if we choose the second mode, that our work vanishes, right? Because this is equivalent to our work here. So the work can't be 0. We know we're applying a load. It's kind of like saying there's a couple things that can't be 0. The work can't be 0, and a sub n can't be 0. Like we can't we're assuming that there has to be some deflection to this beam. We can't look for any solutions that say, oh, the solution is just that a sub n equals 0. Well, that doesn't help us. That is kind of a trivial solution that doesn't tell us anything about the beam. But if we choose an even number for n, then our work would vanish. Does that make sense? Do you see that?
Yes, I got it. I got it. But I was wondering also, so the work is always negative, or this is minus the work?
So it's the work is whatever the work is, but the total potential energy is the strain energy minus the work.
Okay, but in this case, the work alone is negative, or
in this case, the work is positive,
minus.
but we're taking away the work. And it's
Okay,
positive
but in
because
this expression is.
Let me see if I can see why. I think you end up changing signs twice. I think you end up with, if we only keep the odd terms, then we're left with, oops, that was bad. Oh God. If you only keep the odd terms, then that leftmost term there is negative. So you end up, both terms become negative. So then combining them, you end up with a negative number.
So the work is negative.
Well, but that's confused by the fact that I think when you take this derivative here, that we had a negative sign pop up when we went from sine, when we integrated the sine term over from 0 to L, we ended up with a negative term. So it's like negative and negative, and then we ended up back with a positive. That's a good question. And you can calculate that out. Again, for this type of stuff, I think is really useful to visualize with Mathematica. You can kind of plot these terms, this integral looks kind of arbitrary, but it just drops right out if you just plug it into Mathematica. And so I would recommend just playing with that. Yeah.
Okay, thank you.
Mm-hmm. This often ends up yielding systems of equations that can be solved simultaneously. It often is really useful for solving buckling points. So when is something going to buckle? And those buckling points, you end up learning about buckling in mechanics of materials, and it's like, let's just focus on the buckling of a column that I load. But oftentimes, when you're talking about engineering structures, you might have a frame or a truss or some sort of a system with kind of multiple points that could buckle in multiple directions. And the question is, well, how's that structure going to buckle? That's not quite as straightforward as just looking at evaluating the buckling of an Euler column. But the Rayleigh-Ritz method here is really powerful for allowing you to kind of solve for these buckling modes in these systems where there's kind of different possibilities for the system to buckle in different ways. So in terms of structural analysis, you can be really good at approximating those critical points. All right, this is all I wanted to cover for today. Last class lecture will be posted online in a couple of hours. The notes from last class will be posted online. I'll send you a link with the video, the notes from last class, and a Mathematica notebook from last class. I'll also be posting this video once we're done here, along with, I'll send you these notes. And I don't know if I have a Mathematica notebook for this one or not. But what I'm going to do is put together a big kind of set of problems for you to work on all these approximate energy methods, Castigliano, Fourier series, and the Rayleigh-Ritz method. And if you have any questions, feel free to reach out to me or Jeff, and we will happily help you navigate this.